All right. So we've been talking about sequences, our lists of numbers, and we were doing example, excuse me, examples like this where we have an explicit formula for our sequence, and we can write out the terms if we want to, right? So I've just done a little example there. I'm going to do a couple of examples of moving in the other direction where we're given a sequence and we want to try to write an explicit formula for it. So let's start with this one. Actually, let's start with this sequence. Let's make it 0, 2, 4, 6, 8, 10, and so on, right? So here we have the sequence of non-negative integers, sorry, even integers. And so we want to index, right, where we're going to have, right, since I have a 0 here, I'm going to start indexing at 0. This would be A0, A1, A2, A3, I don't know why I wrote so many, A4, A5. And we want to come up with a general term, the nth term, right? And it's there's not necessarily a rule, there isn't a rule or a set of steps I can say that will get you there. We'll come up with we'll see a few patterns emerge that we'll like to use, but we just need to notice here that if we're indexing starting at 0, each term is just twice the index, right? Twice 0 is 0, twice 1 is 2, twice 2 is 4, twice 3 is 6, and so on. So this sequence, or this sequence can be written explicitly as 2 times n, right? Where we're taking n, we're just starting n at 0, okay? Let's do the next obvious one, which would be the sequence of odd integers, right? This one's not quite as obvious what to do, especially if we hadn't just done the even integers, but right, there's nothing you can multiply like doubling a number multiplying by 2 to get all the evens, but we do know that our odd integers are always just one different than an even integer, right? 1 is just 1 above 0, 3 is 1 above 2, 5 is 1 above 4. So if we look at the work we did above, it's pretty easy to say, well, why don't we just take those even integers and add 1 to each of them, right? Again, starting at 0 and so on. And this is another one where, and so for one, we want to remember this pattern. Having even and odd things is something that will come up repeatedly down the road. And so just having these in your wheelhouse, right? In your set of tools, we know that we can just take 2n for the evens and 2n plus 1 for the odds. It's also convenient to note that sometimes we might want to write the odds this way, as 2n minus 1, and just start our indexing at 1 instead of 0. Right? But same thing will happen. You take 1, double it, you get 2, and subtract 1, you're back at 1. Take 2 and double it, you get 4, minus 1 is 3. You'll get the exact same sequence, we're just indexing differently. Part of the reason we sometimes have to index differently is, this will be something that's happening way down the line, but you're combining sequences or eventually series, and you're trying to match indexes. And so if one's written one way and one's written another, being able to kind of shift around a little bit and still come up with the same sequence is important. All right, let's see. Let's do another one. Let's get a little trickier here. So here's a sequence, 10 thirds, negative 29ths, 40 27ths, and negative 80 over 81. So first of all, it's not maybe obvious that there's a pattern here, though there seems to be a pattern. We'll do a little work to get that, but let's assume that there is. We want to build an explicit formula that would tell us, like, if I wanted to know the 10th term in this, could I write it down? So there's kind of a lot going on in this. And so one thing to do, notice that this is an alternating sequence. All right. And we already saw how to get alternating sequences in the last video, right? You have a -1 to a power of n, or -1 to an n plus 1 uh, depending on whether you want the beginning, how you index it and stuff. So I'm gonna throw that information away for now. I'm not gonna worry about the positive negative part. I can add that on the end. So right now I'm just gonna think about these terms, just the values that we have here. Okay. And I'm going to think about we're going to start with some obvious ways in which we might get from one term to the next, right? And again, there's no algorithm or no set of steps I can tell you that's always going to be the thing that works. We just have to have a lot of tools, and just with practice, you'll start to get some intuition. So, two of the big ways we get from term to term is often we're adding between terms, adding or subtracting, or multiplying or dividing by some factor, right? When I look at, if we're adding by something, if we're going to be adding by the same thing each time, it's going to be pretty obvious, right? You'll see things like 7, 11, 15, 19, 23, right? There's a difference between 4 in each of them. If you quickly inspect this one is about 29ths is about 2, 10 thirds is about 3. So there's a difference of about 1 there. But then 40 27ths is we're not seeing that same difference, and then is a little less than 2, and then 80 81st is just under 1, and so there's not the same difference. So it's pretty quick to see that we're not adding or subtracting something. Multiplying, however, we might notice something happening here, right? Looking at the numerators, I can see that each time they're doubled, right? If I multiply this by 2, I'll get the next one, right? And in the denominator, if I multiply by 3, I get the next one, right? So I'm just writing this out, and we're just going to notice, like, to get from 10 thirds to 29ths, you multiply by 2 thirds, because that gives you 29ths. And then to get from 29ths to 40 27ths, you multiply by 2 thirds again and 2 thirds again. So that seems to be the pattern. That seems to be what we want. That our term, let's see, how can we write this? Is going to have a factor. Where's my pencil? Oh, there we go. Is going to have our, let's start building our term. All right. Let's see. I'm going to put, we talked about the negative. We're going to deal with that. It's going to have some indexing. I'm going to leave it blank for now, and then we'll go back and figure that out. I can also see it's going to have a factor of 2 thirds, right? And that each time n increases by 1, we get another factor of 2 thirds. So this 2 thirds to the n will do that. When n is 1, we get one factor of 2 thirds. When n is 2, we now have another factor of 2 thirds. When n is 3, we have another factor of 2 thirds. So that should cover that. And then finally, well, what's missing right now? If I put in n equals 1, I'm just getting 2 thirds, but I want 10 thirds. So it seems like we also need another factor in here. I would have to multiply that by 5 to get what I want, right? And then we'll check in a second to see if it works. Let's deal with the negative now. So we want our first term to be positive. If we do a to the n, I'm going to start my indexing at 1. That's how I've been figuring this all out. If I leave it as n, when n is 1, we'll have a negative, so I need to shift that by doing +1 there. Right? So let's just give this a check to see if we did the right thing, right? When n equals 1, our negative 1 is squared. We get 2 thirds times 5 equals 10 thirds. That's the right first term. Let's look at n equals 2. We'll now have a negative 1. We'll have 2 thirds squared times 5. So this is going to be negative 4/9 times 5, or negative 20/9, right? And that's what we wanted. And so you can check the next couple, but it will continue to work. And so that's the expression we want, right? You could decide to simplify this a little bit, not really so much actually. So I'm just going to leave it like this. So in any event, right, that's a bit more complicated, that one. It's not as obvious when you start, but this looking for factors is a common tactic, one of a common factor between terms, or a common difference, right? If we could also think of, we can look at the odd integers as we're adding 2 each time, right? And that's kind of what when we multiply by 2, that's what you end up doing as it increases each time. Okay, let's see. Let's leave it there. I think I want to get into another type of series, that or sequence, that we haven't talked about yet. Let's go back to the Fibonacci sequence. All right. So some people started at 1, sometimes we started at 0. Either way is fine. So I'm just going to do it this way. Right. So if you haven't seen it before, Fibonacci sequence, you take two terms. Each term is the sum of the previous two terms, right? So this one, the third term, the second one we see is a sum of 0 and 1. And then the 2 is the sum of 1 plus 1. And the 3 is the sum of 1 plus 2. 5 is 2 plus 3. If we did the next term, it would be 3 plus 5 is 8. Then 8 plus 5 is 13, and so on, right? I believe we can write an explicit formula for this if you wanted to know what the 50th term is, but I don't think it's easy to come up with that. I certainly don't know how to do it off the top of my head. But what is easy to do is write our sequence in a different way, what we call a recursive definition. So in a recursive definition, what we mean by that is that the next term, or the second to next term, or something, to get each term, you have to refer to the term before, right? That to get the third term, you might have to look at the second term, or in the case of the Fibonacci sequence, to get a term, you have to look at the previous two terms. That also implies then you can't just kind of start without having a previous term. So when you have a recursive definition, you need to give in this case, I need to give two terms. A naught is 0, A1 is 1. And then I'll give the definition. A sub n is equal to A sub n minus 1 plus A sub n minus 2. Okay? So let's think about what that's saying. The nth term, well, if we're looking at the nth term, the n minus 1 term is the term before, and the n minus 2 terms is two terms before. So we're saying the nth term is the sum of the previous two, right? And this is why we have to give two terms here, because if I gave you nothing or one of them, we wouldn't be able to follow this formula. But with this formula, I have A naught is 0, A1 is 1. If I want to come up with A2, my formula tells me that's A1 plus A0, or 0 plus 1 or 1. And then when I want A3, my formula tells me that's A2 plus A1. So that's going to be 1 plus 1 or 2, and so on and so forth. And so this gives us our, this gives us the sequence if we just keep adding them. Let's do an example of a recursive definition where we only need one term. So for example, I can write A naught is equal to 2. And the nth term is twice the previous term plus 1, right? And so to get each term, right, I'm starting with 2. The next term is going to be twice that. For plus 1 is 5. Then I'm going to double 5 and add 1, I get 11. Double that and add 1, I get 23, and so on and so forth. Also notice with this definition, I can use the same definition. Let's use B. But if I just start with a different number, I will get a different sequence. So the recursive definition looks almost the same except for that starting term. So here we'd start at 3, double it and add 1, we'd get 7, double it, add 1, we'd get 15, double it, add 1, we get 31, and so on. Okay? But in both cases, those are recursive definitions. Okay, that's all I wanted to say about recursive definitions. We will see less of those. I've used them a lot less in my mathematical career. My guess, as someone who does not do any program or very little programming, is that they show up. The little programming I've done, I've used recursive definitions often in that context. So I imagine this is something that we see in computer science more, but that's just a guess. Okay, one last thing I want to do is we're going to look at some notation, and this is one of those things that it's pretty hard to explain right now, but it turns out that in our study of sequences and series over the next few courses and on, the factorial shows up quite often. So I want to make sure we all know what a factorial is and get a little bit of understanding how we can manipulate them. So factorial, first of all, I'm going to give you the first couple of them. The factorial is this exclamation point, and 0 factorial is going to be 1. 1 factorial is also 1. And in general, n factorial is n times n minus 1 is n minus 2 all the way down, to 1, right? So you take an integer like 10 and you multiply by 10 times 9 times 8 times 7 times 6 and so on, all the way down to 1, right? You know, the question of why does 0 factorial equal 1 often comes up. One answer is just that's the way we define it. It works out conveniently to have it that way, which is totally true. But it's also true that it makes sense in a lot of different ways. One way is the factorial shows up. One place it shows up very often is in something called combinatorics, which is I like to call fancy counting. And so one thing you might want to do is, like, if you have a deck of cards and you want to know how many different ways can you arrange it, the answer to that question turns out to be 52 factorial. 52 times 51 times 50 times 49 and 48, all the way down to 1. It's a massive number, right? Or if you have, let's look at a simpler case. Let's say I have 3 letters, A, B, and C. The number of ways in which I can arrange these is 3 factorial, or 3 times 2 times 1 is equal to 6, right? Let's just see these really quick. We'd have A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A, right? And those are all the different ways we'd be able to arrange those 3 letters, right? So in that context, 0 factorial is how many different ways can you arrange no things? And if you have to have an answer to that question, which is reasonable to do, like, there's just one way, there's just the no things. You can't put them in a different order. There's just nothing there. And so that makes sense. But it's good enough for us to just think it's a definition. It works out conveniently that way. Okay. So anyways, back to the factorial, right? So for instance, 5 factorial, just to make sure this is clear, if this is the case where n is 5, then n minus 1 is 4, then n minus 2 is 3, n minus 3 is 2, and n minus 4 is 1, all the way down to 1, right? Which turns out to be what? 5 times 4 is 20, times 3 times 2 gives me 120, okay? So we will see sequences in series that use the factorial a lot. So let's just see a sequence using it right now. For example, 2 to the n over n factorial, right? In this case, we'll take this to be, we'll start at 0, right? So let's look at what this sequence looks like. A naught, putting in 0, is 2 to the 0 over 0 factorial, or 1, right? 1 over 1. A1 is going to be 2 over 1 factorial. 2 over 1 is just going to be 2. A2 is 2 squared over 2 factorial. So that's, I wrote something weird. Oh, I wrote something weird in my notes. I skipped a number. So anyway, sorry about that. 2 squared over 2, let's just write it out. 4 over 2, 2 again. A3 is going to be 2 cubed over 3 factorial. So this is going to be 8 over 3 times 2 times 1. 8 over 6, or 4/3. But actually, let's write it as 8 over 6. Show you why in a second. A4 is going to be 2 to the 4th over 4 factorial. So 2 to the 4th is 16 over 4 times 3 times 2 times 1, 16 over 24. And then let's do one more. A5 will be 2 to the 5th over 5 factorial, or 32 over, we just did this one, as 120. Okay. So first of all, we get our sequence. Right, it looks like 1, 2, 2, 8 over 6, 16 over 24. I know I could reduce these, but I want to make a point. Hope, right? Let's just even do one more just to see. A6 is going to be 2 to the 6th over 6 factorial. So that's 64 over 720. 64 over 720 and dot, dot, dot. Okay. So one, we're just getting used to using factorials here. But two, I want to notice something about the factorial. We've got an exponential in the numerator here. One of the big things about exponentials is how fast they grow, right? We've compared them to polynomials and seen that eventually exponentials, if their base is bigger than one and their exponents are positive, it's going to grow much, much faster than a polynomial eventually. We've got a new kind of thing here, this factorial, and if you notice what's happening in our denominators, the denominator is growing much, much faster, right? The denominator started out smaller. Well, they started out even, 1 over 1. Yeah, let's put these back in. 1 over 1, this was 2 over 1. The denominator was smaller, then we got 4 over 2, the denominator was still smaller. 8 over 6, the denominator is smaller, and then suddenly the denominator is a bit bigger, a lot bigger, and then much, much, much bigger. And the next one's going to be even more so, right? We're going to have 64 is going to get doubled to 128, and we're going to have 720 times 7, so we're up around 5,000, right? And when you multiply by that by 8, we're going to be in 40,000, where the doubling is still going to be down in the hundreds. And then we're going to be multiplying by 9, so 360,000, is that where we're at now? I can't remember. Anyways, we're getting up very quickly. Factorials grow incredibly fast, which is an important feature of them in dealing with sequences and series. But for now, I just want us to note that. One last thing I want to do with factorials is just an example of a computation that we'll see things like this at times. We'll end up with something like this, right? And when you're new to these, this looks pretty maybe just confusing or just mysterious. But let's think about what this is. Let's just do an example off to the side. If n is equal to 5, what we have is n plus 1 factorial, 6 factorial, over n minus 1 over 4 factorial, right? Now, we can multiply those out. We just did 6 factorial is 720 and 4 factorial is 24, and then we could divide. Or we could notice this. 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Since everything's being multiplied, we can cancel those factors and we end up with 30. But the important part is we're ending up with 6 times 5. Let's do a similar game here. N plus 1 factorial means start with n plus 1. Oops, sorry, I'm not doing factorial now. Multiply it by the number below that, which is n. Multiply it by the number below that, or the integer below that, n minus 2. And you just keep doing that until you get down to 2, down to 1. N minus 1 factorial means start with n minus 1. Multiply it by the number below that, n minus 2. Multiply by the number below that, n minus 3. Keep going down to 2 times 1, right? This is going to cancel. This is going to cancel. There's an n minus 3 in those dots. The 2 and the 1 all cancel. And so at the end of the day, or the end of the computation, we're just left with n plus 1 times n, right? Which is not nearly as mysterious or difficult to compute, right? Especially, right, we did we did n equals 5 over here. Even if we had just computed this straight away, it wouldn't have been that horrible. But if this was n equals 50, that's a much different computation, but with this form, we know it's just 50 times 51, right? So 2,550. But in any case, we just want to start getting used to factorials, and we're going to do many kinds of computations like this, where we just have to remember what it is. It's just a list of integers, and if they're being multiplied, and so we've got factors over factors you can cancel. Okay, that is it for this one. Thanks, everybody. I'll see you next time.